Hello and welcome to today's lunchtime lecture, the 6th of July 2024. Today we're going to talk about basic and enhanced containment. My name is Brian Thornton. I'm a UAS inspector with the IAA UAS division. This lunchtime lecture will take about 30 minutes to get through some of the elements of basic and enhanced containment, and approximately we'll get through 30 slides. Okay, so I hope you enjoyed today's lecture, and then we hope to also continue this lecture series as we get more feedback about what other operators and industry would like us to present on. So a quick overview about what we're going to discuss today. So because there's a broad, diverse background of industry experts to hobbyists and professional UAS operators, the first approach is to talk about UAS specifically category operations with regards to kind of a general overview to give people a flavor of what we're talking about and where containment applies. Then we'll briefly get into basic containment and what it is. We'll move on to enhanced containment, and we'll talk about means of compliance like UAS 2511 containment. And then finally, we'll talk about containment and alternative means of compliance. So what that means is that EASA can prescribe means of compliance, but operators and industry and competent authorities around EASA member states can also provide alternative means of compliance to meet enhanced containment requirements. So as always, with aviation in general, we go back to the base regulation and what regulation applies. In this instance, with regards to operations in the specific category, we talk about Article 3 of EU Regulation 2019-947. And we're talking about the categories of UAS operations that apply to the regulation. So if we move to Part B of Article 3, it states that UAS operations in the specific category shall require an operational authorization issued by the competent authority pursuant to Article 12, or an authorization received in accordance with Article 16. Okay, it goes on, but that's the high-level review of where the regulation is, and it's available to everybody on the EASA's website. So UAS specific category operations containment requirements. So in the UAS specific category, there are a variety of approvals that applicants can seek from the competent authority. Okay, the first one being standard scenario. So you submit a declaration to the competent authority and they review the application declaration. The second one is predefined risk assessments, and these can be submitted to the competent authority for an operational authorization to operate in a specific category. And then finally, the third one is a specific operations risk assessment, SORA. Again, you submit it to the competent authority for an operational authorization. And what I would like to get through today in this part about kind of operational overview in specific category is what best suits your operation. Does an STS, a PDRA best suit your operation? And in that, where does containment lie? And what are the requirements for each of these specific category authorizations? So let's get into a bit about operations in the specific category. We'll just have a quick general overview for the audience that will listen in today. So operator considerations, containment. Okay, we like to kind of have this discussion with applicants when they come to the authority about what they're looking to do. So you might ask the question, what UAS operation do I want to do and why? Where do I want to conduct my operation? How will I achieve this and the technical means by which I'll do this? So the technical means is kind of the UAS, the whole system, the remote pilot station, depending on the operation and the level of intricacy and so on. There's a wide variety of UAS systems out there. But then also we have the safety mitigations, and we'll get into that a little bit later. So when do you want to conduct it? Could be time of day, it could be weekends only, it could be nighttime. before dawn and so on. And then we can also consider other limitations, mitigations, ground and air risks. So the first question we might ask, does the operation fall under the open category? If not, okay, and you've reviewed your concept of operation or what operation you would like to conduct, you might consider that the operation can and must only be conducted within the specific category of UAS operations. So that's where we come back to the questions. Is the operation covered by a standard scenario? Is the operation covered by possibly a predefined risk assessment? Or if it doesn't meet the criteria, you might elect to consider a specific operations risk assessment that you conduct. SORA is within the regulations. There's guidance in the easy access rules. There's 10 steps of how to conduct a SORA review, and applicants can do that. But these are just some flavors, some thoughts about how you might consider what type of operation and what type of authorization you might look for from the authority. And consequently, what are the containment requirements for each of those different areas within the specific category operations? Does the operation fall in the certified category? Probably not, but maybe in the future it will. And then lastly, point 6 there, is the operation subject to a specific no-go from the competent authority or other stakeholders, for example, AirNav Ireland, GeoZone. So you may be aware that across Ireland and other EASA member states, there are geographical zones that may prohibit or restrict UAS flight operations. So for example, aerodromes, airports, places of national critical infrastructure, they can be blocked off by geozones. So again, that's a consideration before you elect to apply to the authority or want to operate it in a different type of specific category operation. So briefly, I'll just talk about the semantic model. And essentially, easy access rule prescribe the semantic model as a methodology to assess the ground risk and assess the air risk. I think this is a good representation of this pictorial is a good illustration is a good representation of a lot of text within the easy access rule and what they mean by air risk and ground risk. So you can see on the left-hand side, we've got the ground risk model. On the right-hand side, we've got the air risk model. Okay, so there's two elements to a US operation, and what risks can apply or can be affected by you flying your drone, okay, or flying your UAS. When you consider in that vein, ground risk and air risk, you want to operate somewhere in the middle of that, and that's your flight geography. You want to operate in an area where you know your aircraft can operate safely in some airspace above some topographical area. Outside of that, the semantic model prescribes a containment area. So in the event that your drone might leave the flight geography because of loss of control or whatever, you can contain your UAS to the containment area. What that means is that the UAS operator will have to do some action within the containment area that if it is to leave the containment area, your drone will land within your ground risk buffer. And you will see in the ground risk model, the ground risk buffer can apply to, say, for example, an area whereby if there's a loss of control, your drone will land within that area that you have measured and you have consolidated within your flight plan. Likewise, the air risk model then, if you were to have a breach of your flight geography, the UAS is in the containment area, there's a way or there's a mechanism to possibly terminate the flight whereby your UAS will land within your operational air risk buffer. So essentially, within all of that, anytime you may conduct an operation, you have a way or a means to mitigate the UAS from encroaching the adjacent surrounding areas or encroaching in the adjacent airspace. And we'll get into that a little bit more. And there's ways and means to prevent your UAS from leaving your operational volume. So we talked about standard scenarios. And again, Article 3 prescribes the different types of UAS operations, and standard scenarios is one ways of achieving operations in a specific category. So you can see on the left-hand side, we have STS-01, and below that, STS-02. I'm not going to get into the detail of what that really means, but you might know VLOS, BVLOS, and the differences. So for STS-01, it means conducting an operation within visual line of sight. That means that the operator, the remote pilot, can see the UAS at all times. And following that, we have STS-02, so an application to the competent authority for STS-02 means that the operator, the applicant, wants to conduct an operation beyond visual line of sight. Okay, so that's just a brief overview of what standard scenarios are. So a standard scenario is essentially a pre-baked risk assessment that's been conducted and prescribed within the EASA regulation that you can follow this prescribed method, develop an operations manual, and submit that to the competent authority. Likewise, predefined risk assessments were the precursor to STS. There's 5 different scenarios: PDRA, S01 and 2, and then there's PDRA G01, 2, and 3. And again, without getting too much into the detail, again, it prescribes, I'd like to say, a pre-baked risk assessment that operators can apply to their operations manual, apply to their operation. And similarly with the STS, there's a breakdown between VLOS and BVLOS operations and the requirement therein. So when I talk about the regulation, this screenshot here is just an example of the PDRA S01 characterization and conditions table. What that means is that there are a number of conditions and characteristics that apply to your operation that you must make declarations for within your operations manual. And regarding and relating to containment, we have prescribed requirements for applicants and operators to meet basic and or enhanced containment depending on how you conduct your operation. This is just an example. This is prescribed for STS 01, 2, and for all the different flavors of PDRA. Okay, so you go to the regulation and you see what the containment requirements are within that. And then finally, I briefly discussed SORA. SORA step 2 and 3 relates to ground risk. Okay, so step 2 is the determination of the UAS intrinsic ground risk. You might remember I stated that SORA is a methodology or a tool for operator applicants to go through steps 1 to 10 to try and determine and verify the risks associated with their operation. It's a methodology that operators can follow. Likewise, you need to develop your operations manual. But more specifically, step 2 allows operators to determine their ground risk and apply a value, an integer value against that risk. So depending on the type of operation you might conduct, whether it's in a rural or more populous environment, there is a scoring against or a weighted score against the risk observed against that type of operation. Once you've identified that, you move on to step 3 of SORA, and then you can determine your final GRC. So you can apply some mitigations, okay, against your initial ground risk. And then once you apply mitigation, you can in fact reduce the risk, and consequently the value, your integer value in that risk matrix is reduced. Okay, so it's a very prescriptive method of applying a mitigation to your operation, and then consequently getting this integer value in your metric where you can employ through your SORA methodology. Why am I talking about steps 2 and 3? Because steps 2 and 3 feed into your mitigations, which feed into your mitigations for your adjacent airspace. So this is just a lead in to SORA step 9, and we'll discuss that later on. So you might ask, what type of mitigations do we have with regards to step 3 of SORA? So the final GRC determination is based on the availability of mitigations to the operation. So potential mitigations and correcting factors are below. So we see the mitigation for M1 is a strategic mitigation for ground risk. So M1 mitigation is meant as a means to reduce the number of people at risk. So that applies within your operational volume, but it also applies to the adjacent area and to the adjacent airspace. Step 2 is a means. Okay, this mitigation means is meant to reduce the energy absorbed by people on the ground. M2 mitigations for the purpose of this lecture is just by way of information, and we'll focus more on M1 mitigation because what we're trying to do with containment, both basic and enhanced containment, is that we reduce the number of people at risk on the ground. So from the regulation, we have developed this table to kind of encapsulate the different types of mitigation. The robustness, meaning is it low, medium, or high, and where it applies. For low mitigation, you can see the description criterion, integrity, and the assurance. We're more concerned with regards to medium robustness for enhanced containment, where we define the ground risk buffer, what might happen within the ground risk buffer, the integrity level, and how do we assure that this level of mitigation can be applied. So this might be applied or declared through evidence of testing, analysis, simulation, or inspection. And if you recall earlier, I mentioned MOC 2511. Medium M1 robustness is outlined in that document, and that means of compliance has been published by IASA. And again, we'll talk about that a little later on within the lecture. So basic attainment, okay? Just that was a brief view on operations in the specific category. We talked about STS, PDRAs, and SORAs, and a little bit about containment. But that's just an overview about how it applies to the specific category. More specifically, basic containment. Again, a reminder of the semantic model. We want to fly our UAS within our defined flight geography. If the UAS departs the flight geography, we are now in a containment area that has been measured and prescribed as outlined in the operator's operations manual. An action must happen within the containment area that if the UAS is to leave the containment area, it will land within the ground risk buffer and the people at risk on the ground is reduced. But also beyond that, we must consider the adjacent area and the adjacent airspace. So with regards to the regulation, specifically 947, right, the objective is to address the risk posed by a loss of control of the operation, resulting in an infringement of the adjacent areas on the ground or the adjacent airspace. These areas may vary with different flight phases. Therefore, a requirement for UAS containment within the ground risk buffer. That's the premise of specific category operations, that if we do have a loss of control, if we do exit our flight geography, we have a procedure in place that we can potentially, using a mechanism, bring down our UAS within the ground risk buffer, but we've mitigated because we have reduced the number of people at risk on the ground within our defined ground risk buffer. So the definition of basic containment: no probable failure of the UAS or any external system supporting the operation should lead to an operation outside the operational volume. What that means is when we fly our UAS, the intention is to always keep our UAS within the operational volume. The competent authority may accept a declaration for the claimed integrity. Yet the applicant declares that the required level of integrity has been achieved and supporting evidence is available. Basic containment applies to all UAS operations, and there's a caveat there There's always a corner case where containment might not apply, but again, for the context and for the purpose of this lecture, basic containment applies for specific category operations. Regulation 947 alludes to the operational volume, and I've made mention to the operational volume. So essentially, the operational volume is your flight geography, which has lateral and vertical limits. And likewise, your contingency volume has lateral and vertical limits. Now, in this illustration, it's prescribed in a spherical manner. It doesn't always have to be like this, but it's just a purpose. The purpose of this diagram is to show I mean by the flight geography, the contingency volume, and then your groundless buffer. When you conduct your operations in a specific category, these are defined. And that how you define that procedure is outlined in your operations manual by the operator. So the operational volume is comprised of flight geography, contingency volume, and your groundless buffer. We have some guidance on the IAA website. You can see UAM 008 in our publications page, which talks about how to define the operations volume and what it is. Okay. So basic containment is when we fly a drone, essentially we will contain our drone to within the groundless buffer. For operations in the specific category, enhanced containment applies also, and we can make a declaration to that. The means of compliance has been published by IASA, and we call that Light UAS 2511 containment. And this is for, if you remember, we talked about the M1 mitigation. We had low, medium, and high levels of robustness. This applies to medium risk. Okay. So again, going back to the extant regulation, enhanced containment. The enhanced containment applies to operations conducted. One, either where the adjacent areas contain assemblies of people, unless the UAS is already approved for operations over assemblies of people. Or ARC-D, unless the residual arc of the airspace are intended to be flown within the operational volume. So if you go to the first point of number one, contained assemblies of people. So enhanced containment applies where if you, as an operator or an applicant, intend to operate, for example, in a populated environment, and there is a football stadium near your area of operation, you need to consider that within your risk assessment for conducting that operation. If you have a football stadium adjacent to your area of operation, well, most likely enhanced containment applies. Okay. Similarly, ARC-D would be considered high risk airspace. So ARC stands for Air Risk Classification. D is the level of risk appropriated to that airspace, whereas A would be the least riskiest. So ARC-D could be considered operating near an aerodrome, an airport, and so on. So part one there talks about adjacent area, which is the ground, and the adjacent airspace, which could be ARC-D, which is your airspace. So again, the semantic model, we're looking at the ground and the air risk. Part two then, or where the operational volume is in a populated area where M1 mitigation has been applied to lower the GRC, or operating in a controlled ground area. If you recall, I alluded to M1 mitigation, which could be applied to step 3 of SORA. So we can see the connection between step 3 of SORA. We will move into the adjacent airspace, step 9 of SORA, but how it's linked to enhanced containment and the means of compliance as published by IASA in MOC 2511. So that's a good lead into my next slide. And step 9 of SORA considers the adjacent area airspace. Again, this is taken from the regulation 947. On the upper left side, we see the requirements for basic containment. On the lower right side, we see the requirements for enhanced containment. I will follow on and we'll discuss primarily enhanced containment. So again, we are still within the structure of 947, and we discuss enhanced containment for adjacent airspace and the area. So what do we mean by definition of enhanced containment? The probability of the UA leaving the operational volume should be less than 10 to the minus 4 flight hours, and no single failure of the UAS or any external system supporting the operation should lead to its operation outside the ground risk buffer. Compliance with the requirements above should be substantiated by analysis and/or tests with evidence. So 10 to the minus 4 flight hours, what that means is that there's a probability that your UA will have a loss of control outside of the ground risk buffer once every 1,000 hours or 10,000 hours. 10 to the minus 4. Leading on from that, for UA with a maximum characteristic dimension not greater than 3 meters, operated up to Sail 2 operations, the competent authority may accept a declaration from the applicant for compliance with MOC Light UAS 2511. So 947 prescribes a means of compliance to MOC Light UAS. If you present a declaration to the competent authority may or may not accept the declaration, depending on the system that you present to the authority. And we'll talk about different mechanisms within 2511 that you might apply to your UAS operation. Again, for UAS configurations exceeding the applicability of such MOC, the competent authority may decide to accept declarations based on the means of compliance with evidence available, or to accept appropriate means of compliance proposed by the applicant. So you don't have to stick rigidly with MOC 2511. As an operator, potentially you are an operator and/or manufacturer, you might determine or develop a system, means, or mechanism, or design some sort of system where you can apply to the competent authority with substantial evidence to support your claim that you meet enhanced containment requirements as those outlined in the regulation, and that may be reviewed, accepted, or not accepted by the competent authority. So there's some flexibility there. Otherwise, the competent authority may request the applicant to use UAS for which EASA has verified with the claimant integrity. And again, we'll talk about that a little later on. Now, we moved from enhanced containment requirements within 947, the extant regulation, and we'll talk now that link to MOC Light UAS 2511. Containment. This is the publication, so you can see it on the right-hand side. It's available on EASA's website, and you can see the link there below. But what this is guidance for FTS manufacturers and UAS operators. It also, they are a variation of FTS systems on the market. So you can see, you might say, well, we've jumped directly into FTS. So what does FTS mean? FTS means Flight Termination System. MOC 2511 prescribes means by terminating the flight. We want, or there could be a need to terminate the flight if we depart the flight geography, and potentially as part of the containment measure, we want to terminate. So in a sense, our UAS will land in the ground risk buffer, and we mitigate the risk to people in the adjacent areas and adjacent airspace. When I say people, I mean systems. It could be assemblies of areas, but it could also mean adjacent aerodrome or airport, for example. So specifically then, within the context of 2511 containment, the methods of termination could be physical motor stop. You stop your motor, the drone will come down. ESC signal stop. A signal from the remote pilot for a battery bus signal stop. Or by way of just discussing flight termination systems, some flight termination systems have parachute recovery systems integrated. So there are flight termination systems, parachute recovery systems integrated into the one system. Okay, we'll talk a little bit more about flight termination systems as we go through this. So again, within the realm of UAS 2511 containments, point one, no probable failure of the UAS or any external system supporting the operation must lead to the operation outside the operational volume. That's the key point. We want to keep our UAS within our operational volume that we have defined and we've measured and we have put into place before we conduct our operation. When the risk associated with adjacent areas or on ground or the adjacent airspace is significantly higher than the risk associated within the operational volume, including the air risk buffer. So if you have the risk is greater on the ground or the airspace outside the operational volume, enhanced containment applies. How can we keep our UAS within our operational volume if we're going to depart our operational volume? The probability of leaving the operational volume must be demonstrated to be acceptable with respect to the risk posed by the loss of containment. No single failure of the UAS or of any external system supporting the operation must lead to its operation outside the ground risk buffer. The next point talks about software and airborne electronic hardware. And MOC 2511 prescribes and states that several of these applications leverage flight termination as methods to address UAS containment. We want to use a system and mechanism to contain our UAS within our operational volume to reduce the risk to people, systems outside of our operational volume. Don't get overly confused about this slide. This is just taken from 2511. I'll try to explain it as best I can, but essentially what it states that for SAIL 2 operations in the specific category, the probability of loss of the flight hours is 10 to the minus 2. So the probability of loss control is less than 10 to the minus 2 flight hours. So what that means is you will have one loss of control every 100 hours. MOC 2511 states that it is considered appropriate to assume that the probability that a loss of control would lead to an exit from the operational volume is at least 10 times smaller than the probability that it would lead to a crash within your operational volume. Therefore, there is an assumption that the probability of the UA exiting the operational volume is 1 times 10 to the minus 3. So one loss of control every 1,000 hours is assumed that you will crash within the operational volume if you use a flight termination system, potentially. When such events occur, the flight termination system is triggered to ensure that the crash would still be kept within the ground risk buffer. As MOC 2511 prescribes, an FTS segregated from the UAS, the probability that the UAS would exit the ground risk buffer and enter the adjacent area or enter the adjacent airspace is obtained as. Okay. The equation below states that the probability of the UA exiting the ground risk buffer is equal to those two variables. The probability that the UA will exit the operational volume, the product of the probability that the flight termination system fails when integrated into the system. So the product of the two variables, 10 to the minus 3 multiplied by 10 to the minus 2, is equal to 10 to the minus 5. Essentially what that means is by using an FTS integrated into your UA in a defined operational volume, when the FTS is integrated into your UAA, but is independently separated from the architecture, so there's an independent means to terminate, that the loss of control outside of the operational volume is once every 100,000 flight hours. So there's a significant increase in safety mitigation. And the level of safety has increased dramatically by the introduction of enhanced containment using a flight termination system. The application of this means of compliance for a sale to operation substantiates, therefore, that the probability of exiting the ground risk buffer for your operation is less than 1 is 10 to the minus 5 flight hours. MOC 2511 containment goes into some design requirements. There's a caveat to this. I will go on to explain the test procedure to determine if a flight termination system meets the requirements of MOC 2511. Good thing for operators, applicants, for the industry in general is there are a number of flight termination systems available to operators, commercial off the shelf, and UAS manufacturers are looking at ways to develop flight termination systems integrated into the UAS, and it's available as a whole system compliant to MOC 2511. So that's going forward. But for the purpose of the rest of this section of the lecture, I will just talk briefly about the types of tests that manufacturers and also operators, applicants can apply when submitting an application for enhanced containment to the competent authority. So the FTS should be segregated from the UAS flight control system architecture. I briefly alluded to that. There's a segregation of the air segment, so that could be your C2 link. Segregation of the ground segment, so the physical triggering of the flight termination system is separate from the control system of your UA. Frequency and frequency diversity also needs to be considered. So FTS frequencies should be separated from the UAS control frequency. So your command and control frequency for your UA. If you integrate a flight termination system, the command and control for the UA and the control triggering of your flight termination system, the frequency needs to be independent. So you've got a system and frequency architecture independency, where one system is not reliant on the other. For UAS manufacturers, for operators that want to conduct tests for a flight termination system, whatever that means or mechanism of that flight termination system might be, MOC 2511 prescribes tests. There needs to be a number of successful bench tests, could be done in the lab, but there has to be 10 successful activation tests. Then when successful tests are completed on the bench or in a lab, the flight termination system is integrated into the FTS and tested on ground. Likewise, 10 activations of the FTS need to be successful, and they have to be performed and evidenced and recorded. If you progress to the flight test phase of your flight termination system, MOC 2511 prescribes the flight tests that have to be done. Flight terminations need to be conducted at a minimum height, 5 times equidistance up to the max distance from the remote pilot, and likewise 5 tests conducted at the max height, equidistance until the furthest distance away from the remote pilot. And then finally, end-to-end activation tests. MOC 2511 prescribes that flight termination system manufacturer, developer, OEM needs to test that flight termination system for the entirety of its life until failure. And all of these tests must be available and presented to the competent authority to show compliance with MOC 2511. And also in all that, flight termination system manual needs to be provided to an operator who might purchase or procure one of these flight termination systems and prescribe flight system integration, but also prescribe potentially maintenance requirements for the flight termination system. So what have the IAA done in this regard? So we've worked with manufacturers, we've worked with EASA, and we've developed a publication UAM 013 again, which is available on our publications website. In that, we prescribe from MOC 2511 what the requirements of a flight termination system is, and in Annex A, we list flight termination systems where we have received declaration of compliance from manufacturers and also the substantive evidence that's required that we just discussed. The good news for operators and for applicants out there, there are a variety of flight termination systems for some models of, you can see DJI aircraft. There's different OEM flight termination system manufacturers, and we expect this to grow as industry grows and the requirement for flight termination systems is recognized across EASA member states primarily, but more broadly in the global context. And we will look to keep this Annex A up to date for people for their visibility, but also we work with EASA to inform them of new and different flight termination systems that we might have discovered through operators and applicants like yourself. Also, there's a link then to the EASA guidance on flight termination systems that you can have a look at. So finally, I want to discuss with you enhanced containment and alternative means of compliance. Again, going back, you might recall that we talked that operators, competent authorities may present different means to meet enhanced containment requirements. And this was done most recently done by the Swiss and German competent authorities, so which would be the LBA and FOCA. So together they presented to EASA an alternative means of compliance for enhanced containment. So the aim was to reduce the requirement for enhanced containment for the adjacent areas and airspace. PDRA S01, STS01 would still require proposed ULTMOC, and air safety and UAS geographical zones would also be considered. So within this ULTMOC, it stated that the following three safety requirements apply for operations. Where a large assembly of people, approximately 20,000, is present within a 1 kilometer distance from the operational volume, unless already approved for operations over assemblies of people. The applicant has procedures in place to check this before the operation. So they define a figure for the adjacent area. They say 20,000 people, the density of people at risk. Where the adjacent areas are populated areas and an M1 mitigation of medium or high robustness has been applied. Medium robustness for M1 mitigation applies to MOC 2511 that if you use a flight termination system. The operation is conducted over a controlled ground area, or the height of the operational volume is above 150 meters. Where the adjacent airspace is ARC-D, ATC or competent authority permit is needed before the operation. So essentially, what the German competent authority, FOCA, have presented to EASA is less stringent requirements on operators to enable them to operate within a defined operational volume, but the requirements are more broadly captured within the ULTMOC, the alternative means of compliance. So during this and the preparation for this lecture, we did receive a question: is the IAA going to consider accepting Germany and Switzerland alternative means of compliance for FTS? And the answers that we have for now for the IAA and the competent authority, the answer is no, as it has no advantage for the operator, majority of operators within Ireland. Because, like I said previously, we have worked with UAS manufacturers, FTS OEMs, to try and develop the compliance documents to meet MOC 2511, and that's why we publish Annex A in our UAM 013. And for the type of operations that are conducted by operators, and in particular professional operators in the country, there are a variety of means of compliance for FTS for enhanced containment. So it's not just that we don't want to apply an ALTMOC, it's the competent authority, the IAA, we feel that there's enough variety out there for operators um, to buy a commercial off-the-shelf product and apply it to their operation. In saying that, if an operator would like to present the ALTMOC to the authority for the purpose of their operation, we will review that ALTMOC and make our own considerations and determinations when considering your operation. Yeah, and the second point, like I just said, however, the operator may propose the ALTMOC if they wish, and we will consider. So thank you for listening to the presentation today. This is the first lecture in our lunchtime lecture series. I hope you enjoyed it. I hope it was informative and helpful. Please provide any feedbacks you might have. We will look to share this with all people that have registered for this lunchtime lecture, but also share it on the IAA website for people beyond today, and you can refer to it back. So thank you again for your time and attention, and we look forward to seeing you at the next lunchtime lecture. Bye.